So we're now finally getting on to the scheduling. So how do we actually schedule jobs to run on all those compute nodes from the login node? So we're finding out all about partitions in this module. So how we split up the supercomputer into different types of nodes, and also how we queue jobs onto those nodes. So what is a job? So a job's a unit of computational work. So a lot of the effort that goes into moving a workflow from a laptop onto the supercomputer is to identify how to split up the work into these sort of portions of compute that get sent to the scheduler and run. And the scheduler is the program that's running on the supercomputer deciding who gets to run when. So the scheduler we use is called Slurm. It's a industry standard used by many of the supercomputers internationally around the world, including some of the largest. So we kind of align with those larger centres. So researchers that work with us that kind of outgrow us can still use the same system up on the largest supercomputers in the world. And you interact with the scheduler from the login node that you log onto, and the scheduler will then execute your work on your behalf on the compute nodes when your time's available. I think I've already mentioned the login node isn't the supercomputer, it's just where we're launching our work from, so you don't run any actual computational work on the login node itself. So how is a job scheduler useful? You can think of it as like a planner. In practice, what it's doing is it has all of the cores of the supercomputer or the GPUs of the supercomputer that you can see there on the y-axis. This is actually a picture of the actual scheduling of the supercomputer sort of 3 generations back. And one of the reasons we use it is that you can really see the resolution of the jobs and of what's going on there quite well. And so it had 19,000 cores, and then along the x-axis there you have 24 hours of it scheduling jobs, and each different rectangle color is a different job that's being run. So you can see it's not necessarily distributing those jobs contiguously. You can see that kind of those 4 yellow rectangles. That's the same job that's being split over a range of cores. And you can see effectively what the scheduler is doing is it's playing Tetris. It's trying to figure out how to place all those jobs and pack them together to get the absolute maximum optimal usage out of the supercomputer. And I think, as we've touched on already, because of the cost of supporting the supercomputer, we want it running overnight, we want it running on the weekend. And so I think one of the most important things to take away from supercomputing scheduling is that a supercomputer is something that will allow you to achieve computation that you couldn't do otherwise, or might take months or years to do otherwise, and it will allow you to get that done in hours or days. What it won't let you do is get it done instantaneously, because you're going to have to queue for it, right? So you're getting the results that would otherwise take you a year tomorrow, and that's what it's doing. So it's really important to not get into a sort of a mindset of I'm going to prep my work, submit it to the scheduler, and then sit there watching it going slowly mad. You got a context switch. You got to have something else to do. Go start working on the paper, work on assignments, have something else to do while it's going through the queue, and then come back later when it's done and then look at the results. Ideally, like start working on more jobs to submit. The best way to get stuff through the queue is just queue more jobs. So in terms of just how the scheduler decides who gets to run, it's based on a little bit on the allocation. So comparatively, while you still have allocation left, you're at a normal priority. If you use up all your allocation, the priority of all your jobs will drop, because the last thing we want to do with the supercomputer is have it idle when there's stuff it could be doing. So if for whatever reason everyone who has allocation left has, or they don't have jobs ready to run. People that have finished their allocation, their jobs can start running. So you can actually go over your allocation by a small amount. Additionally, there's a few things in there around, there's a fair share consideration in terms of it's trying to change your priority of your job so that if you are ahead of other people relatively in your allocation, it'll try and slow you down a little bit. Whereas if you've only used a little bit and everyone's used a lot more, it'll try and speed you up to catch up. There's also the time that you spend waiting in queue. So when you submit your job to the queue, it will slowly gain priority to encourage the job to get through the queue. And finally, the way that jobs get placed on the queue, it's actually easier for smaller jobs to find gaps to run. And so we boost the priority of larger jobs to ensure that the big jobs that are actually kind of the reason why the supercomputer's there can get through the queue to run. And so we have these quality of service levels. As I mentioned, normally it's at normal until you run out of allocation, and then it drops down to low. And so your jobs will only run if no one else is running at normal or higher. Once you've finished your allocation and some, eventually you'll no longer be able to run jobs. And we also have these higher priorities. So up to 10% of your allocation, if you have a paper deadline or some work that's really urgent that you need to get done, you can actually self-select, say, hey, this is actually important. I'd like it to go through the queues quicker. So you get a small amount to, everyone gets a small amount to sort of self-determine what's important. And finally, if there are really important pieces of work, we helped out with some of the COVID-19 research, for example, and so those jobs got the highest priority on the system when that was happening. So there's some terms that the scheduler uses. So there's the concept of a cluster. That's basically your supercomputer. And then within the cluster, it's divided up into partitions. And so these are subsets of resources that kind of map to different types of node configurations, as we'll see shortly. So for the CPU nodes, we have the work partition, which is where most of the nodes are sitting. So most of the CPU work that's running on the supercomputer gets submitted to the work partition and then gets launched out onto the CPU nodes that are sitting in that partition. When the system is busy, it's really hard to get a node, and there's sometimes when you want to just test something or to jump on and interactively step through trying to figure out what's going wrong with your job. And for that, we have the debug partition. So the idea is that there's 8 nodes there that are idle most of the time so that you don't have to wait to get access to a node to try and figure out what's going wrong. Occasionally, we have researchers deciding to run production work in the debug queue, which defeats the entire purpose of having it. So don't run production work in the debug queue. It's there for sort of actively trying to figure out, what's wrong rather than just submitting production work. We then have the high mem partition. So 8 nodes have a higher memory capacity of almost a terabyte. So for certain workflows, they have higher RAM requirements. So you'd submit those jobs to the high mem partition so that there's more memory in those nodes to take advantage of. And we also occasionally have workflows that take longer than 24 hours to run. And so we have a few nodes that allow running up to 96 hours. There's a reason why we don't have the whole system running up to 96 hours or weeks or months. And that's because when you have a system with thousands and thousands of processes in it, the statistical likelihood of something failing becomes non-zero. And so there's always something failing in the supercomputer from time to time. And if we let a large job run on most of the supercomputer for a long period of time, and then maybe a week down the track, suddenly something failed and wrote off the entire work of that job, then it's going to be a whole heap of time wasted. So we have the 24-hour limit on the most jobs to make sure that programs are developed to be able to checkpoint and restart and write out intermediate results and restart from intermediate results, so that if there are failures, it can keep going from where it left off. But there is, I guess, some development work in actually doing that, and so we have the long queue that's just a few nodes for those edge cases where you just need that little bit more than 24 hours. The other advantage of having a 24-hour wall time is that there's always jobs finishing. You're not going to get in a situation where the whole supercomputer is just going to be busy for the next week. I mentioned earlier today the copy petition for those data transfers. So that petition maps onto those data mover nodes that have the better network connections to the outside world. So if you are looking to do data transfer as part of your workflow, you'd submit jobs to the copy petition to do those for you. There's also, you might notice, some radio astronomy related petitions for ASCAP and MWA supporting the operation of those radio telescopes. On the GPU side, we have the GPU petition, which has the GPU nodes in it. There's also a GPU dev petition, which is similar to the debug petition for the CPUs. GPU dev is for doing development work on the GPUs interactively, or trying to figure out what's going wrong with the GPU job. And there's also a GPU high mem petition, which has more memory on, more CPU memory on those nodes. One catch is that for the running time on the GPU petitions is you have a separate project code, which is basically your project code with the dash GPU on it. And that's so we can have separate CPU allocations and GPU allocations on the system. So let's start to have a look at some of these commands. Feel free to log in and follow along. Drag this out. Just going to SSH into the Cetonics login node. Is that still large enough up the back? Yep. So the command I'm going to type is sinfo. All of the Slurm commands typically start with an S, that's short for Slurm. So sinfo is Slurm info. And we get a whole bunch of stuff. So you'll see where there's lots of individual nodes that it'll kind of spill over multiple lines. But if I come back up to the top here, hopefully, what we're seeing is the first column there is the petition. So for example, we see the work petition in the first few entries here. You can see the availability, it's up. There's limits on the jobs in there in terms of the job size. I think that's number of nodes. The time limit, you can see that's 1 day, 1 dash hours, minutes, seconds. The number of cores available, there's 128 physical cores per node in the work petition. With hyperthreading, or symmetric more threading, that's double that for 256. You can see the SCT, I think, is sockets, cores, and threads. So there's 2 sockets or 2 processors per node, each with 64 physical cores. Each core has 2 threads that it can process. And then you can see the state there. So the nodes in the work petition, there's 14 that are down. There's 4 that are allocated, which seems low. There's 376 that are in mixed. 17 are in maintenance. 4 are reserved, which is actually the reservation for this course. And you can see if you scroll down that there's similar sort of information for other, so there's 961 fully allocated nodes, for example. If we keep going, you can see there's MWA, the copy queue, debug, high memory. So you can see there's 7 idle nodes in the debug queue waiting if you wanted to do some debugging. So let's come back to the slides. The next thing we'll do is use SQ, so feel free to type in SQ. Again, it's the worm queue. And you'll get a very long list. Again, back up to the top here. Some Unix commands into the first 20 lines. So you can see in terms of the columns here, we have our job ID. So this is an identifier that's given to every job. If you want to come along and cancel the job later, that's an important identifier to have. There's the username of the person that submitted the job, the account the job was submitted under, or the project. Also the name of the job, so you can actually name your jobs so they're meaningful to you and not just a number. As well as the state, which is commonly what you'll want to go looking at. So these R's here at the top are the ones that are running. Ones that are not yet running has PD for pending. And we can perhaps find some pending ones. Maybe SQ again. So you can see here these ones at the bottom that are pending. Some of them are waiting on a dependency. So these jobs have been set up by the researcher to only run when another job has finished. So they're not running yet because they're dependent on another job that's running. It also provides time estimates of when it thinks your job might start running. Again, take this with a grain of salt. If you're kind of sitting there watching that number, you're going to go slowly mad. It might be that it says that your job's going to start running in 4 hours, but then someone else comes along who hasn't used much of their allocation and has a slightly higher priority, then puts their jobs in the queue and it gets pushed out by another couple of hours. So again, the key to using the supercomputer is to put your jobs in the queue, go find other jobs to put in the queue, and go away and do something else until your work's ready. There are some useful options there. -- petition or -p will allow you to show just what's happening in a particular petition. So if I do an SQ -p debug, you can see just the jobs that are running in the debug queue. You can also do a -- me. That will show you the jobs that you have running. So I don't have any jobs running at the moment. And you can also specify a particular account or project name if you're interested in seeing what other people might be running under your project, or specific users. And you actually have a lot of control over those columns. If you want to customize it, you can check out the help pages for the SQ command, and you can specify specific columns that you're interested in. So I think I've talked about the running state and the pending state. CG is completing, so the job's more or less finished and the schedule is just cleaning things up. F is for jobs that have failed to run. So have a go at the exercise. Can anyone tell me how many jobs are currently queued on Sotonix? Yeah. All right. Did I manage to find the work petition and how many jobs are that one? Anyone else? Yeah, that probably sounds about right. Because, half of them are probably in the work queue and the other half are probably in the GPU queue. So, going. So this next exercise lets you have a look at a job that is running that you've submitted. So it's a bit of a chicken and egg. Like, how do you look at a job that you've submitted without first submitting it? So we're going to cover submitting in the next module, but just follow the instructions here. You're going to want to log in and go to your MyScratch directory with a cd MyScratch. Use the git clone command to clone this repository of training examples. Go into the Supercomputing user training and job scheduling overview directory, and then submit the first job.sh using sbatch. So you just type in sbatch first underscore job.sh, and then try, while that's running, doing an sq -- me to see the job that you're running. May need to run that with a reservation, now that I think about it. Do you have a copy of the slides available that you can look at, or is this the only reference you can see? So if you're following along, it might be worth opening it up and having it there, because I will switch across do that. So I'm going to cd to $MyScratch. Going to directory, intern training. Good. So I've get into MyScratch. I've done a git clone of that repository. And what that's done is it's downloaded from GitHub the training examples to my local directory here. And then we can go into that directory. So if you have trouble doing the git clone and it's asking for a password, it's usually a sign you've got a typo in it. it should just download straight away. So to SBatch the job, you could just do a SBatch first job.sh. This will just put it into the work petition, I think, from memory. We actually have a reservation for the course, which will allow us to bypass waiting in the queue. And so to use that, you'll need to do a -- reservation Pawsey intern bootcamp. And if you are not on a course account, then you probably won't be able to make use of that reservation. Or for me, I need to specify the account. So if you want to have a look at the reservations on the system, you can do an S-control show reservation. Just going to go and grep turn in it. Pawsey interns bootcamp. There we go. So by specifying that reservation, that's put it into those reserve nodes that we saw in SInfo, rather than just going into the queue and waiting in line. Depending on how busy the system is, because it's just a very small job, it might be that it just finds a space and runs, even if you're not using the reservation. But while that's submitted, if we do an SQ-me, hopefully you'll now see that you've got a job there that's either queued or running if you're quick enough. I think that particular job sort of sits there for a minute or two, waiting. Hands up if you've run a job. Okay, I'll take that as we're doing pretty good, and we'll keep going. I lost my... Oh, there we go. So, the output you should expect to see. And that brings us to the end of this module, which was how to look at the petitions, look at the jobs that are running on the system. So the next module we'll kick on to will be how to submit jobs in more detail. Are there any questions at this point? Question's a good question. You want to grab the mic?
Just a quick one. There was like a warning on one of the slides, and it was like, do not run like preparatory or test on the like GPU dev or something. I can't really remember now. Yeah, I just wanted to like, could you like clarify what it means? Like, don't run preparatory test runs.
Yeah, so we had an issue where in certain types of simulations, you need to run some fairly computationally intensive jobs to kind of get a feel for whether the simulation is going to your larger simulation is going to run appropriately, or maybe a subset of parameters that you run first before then doing something at a bigger scale on the one that is the best. And we found that that particular type of work was being run by some researchers in the debug queue, and it was just sufficiently computationally intensive and enough of them that it was just swamping the queue and no one could get access to the debug queue. So what you should be thinking when you're thinking, should this be running in the debug queue, is this something where I'm interactively debugging something that's actively going wrong? Am I developing sort of doing some coding work and needing to constantly compile and rerun on the system that, and most importantly, am I going to be swamping the entire petition so no one else can do anything? The last one, then you probably shouldn't be doing it, right? Because the whole point is you can get a node or two to do something.
Yeah. Okay. Thank you.
Good question.